Welcome everyone for joining us today for this IET Midlands Power Group event. Today's event is on the technical challenges to electric takeoff aircraft, including a focus on the battery and electrical machine design, as well as covering some generic topics around the aircraft configuration and certification. The electrification of air travel is one of the rapidly developing areas of industry and is currently helping to drive innovation in high power density energy storage, power electronics, and electrical machine design for aerospace applications. The Bristol-based Vertical Aerospace is one of the companies leading the way in the development of all-electric eVTOL technology and has had their first flight of their second eVTOL aircraft in 2019. I'm very pleased to welcome Lawrence Blakely, who is the head of Powertrain at Vertical Aerospace, who will be presenting on the technical challenges to eVTOL development. Lawrence has 16 years of experience in aerospace electrical systems, including 12 years in the Airbus group, leading the development of A400M and the A350 electrical system architecture. Just before I hand over to Lawrence, I'd like to remind everyone that there is a Q&A button at the bottom of your screen. So please use that for any questions that you might want to ask during or after the presentation. I'll now welcome Lawrence and hand over to him. Thank you, Lawrence.
Thank you very much, Andrew, and thank you everyone for logging on to listen to me talk about the technical challenges that we face in eVTOL. Now, in an hour, I don't expect to cover all the technical challenges. I hope to give you a flavour of what we face and some of the high-level topics. As Andrew mentioned, please feel free to ask any questions. I'll do what I can to answer after. If there are subjects that I'm not expert enough to answer, then I can take them away and I'll follow up, no problem at all. Just to expand briefly on my career history, as a bit of an introduction, I actually started as an aircraft electrician, doing an apprenticeship at Marshall's Aerospace in Cambridge. It gave me a flavour of the hands-on elements of aircraft installation, but also what is good design and what is not so good design, and that kind of set me up in a career in aerospace. And Airbus gave me a lot of opportunity to move around and really understand how things are designed, and really quite importantly, how you design things to meet the regulations. So we talk about the intent of regulations a lot, so I'll probably just touch on that towards the end of this presentation. I've now been with Vertical Aerospace 3 years. I was number 9 in the company. We're now about 110, growing slightly over the next 6 months as we move forward in our development. Again, I will touch on those timelines as I go through. So I'm hoping now my presentation works. There we go. So Vertical Aerospace. We were founded by the owner of OVO Energy, Stephen Fitzpatrick, and the real basic premise of Vertical is to enable electric flight for everyone. And we need to break that down into things that are slightly more meaningful and from an engineering perspective. And the 3 areas that we've kind of focused on is making air travel personal, on demand, and emissions free. Emissions free, really, at the moment, that leads to electric propulsion, battery propulsion quite specifically. Making it on demand, so that is really driving towards much smaller vehicles that you almost hail like a taxi. I don't think the model will be exactly like a taxi, but that's the kind of ethos. And personal, being it should meet the needs of the public, and one of the big needs here is going to be around noise and environmental impact that aviation is having, not just is it meeting your flight mission needs. So that's really our guiding light for our development. Now, when Stephen set up our company, he was really keen not to just draw from aviation. If you take an already tried and tested system and apply it to a new design, you're going to get probably something that is very similar to what's already out there. And Stephen wants something different. So he's purposely drawn from across the various industries. He himself is from energy. OVO Energy is one of the leading suppliers of renewable energies. He's also an avid Formula One fan, owned a Formula One team for a while, Manor Racing, and he's very keen that we integrate that fast pace and very critical design criteria into our aircraft. If you saw the Formula One at the weekend and a pretty high impact crash and the driver steps out and walks away, that's some pretty impressive engineering and pretty impressive design capability. And the driver's obviously very pleased that the F1 engineers are able to design a very lightweight but strong and resilient structure. And we want that in our aircraft quite clearly. So far, so I joined at the end of 2017, actually just after the initial what we call the POC, proof of concept, had been built. I did a small amount of rework on the electrical systems, but not so much. Really, the credit goes to the 6 engineers that started the company to pull that that prototype together. It flew really well, actually. It's now parked at our facility. It's not a product we want to take forward. It was about developing a capability, and really the challenge there was integration. It was off-the-shelf components and pulling those together into a vehicle and integrating. I'm going to talk about integration quite a lot as I move through my slides, and integrating those systems into a vehicle. We then decided that the technology was essentially ready to take some steps into creating more robust vehicles. So a bit of a recruitment drive. We're now at 30 plus engineers, and we are designing Seraph during 2018. Seraph really focused on taking a step forward. There's now some bespoke areas of this design. I will touch on Seraph in a bit more detail in just a second. We then flew Seraph in 2019. Now we're really gaining momentum. We were at 70 plus engineers, and by the end of 2019, we've acquired what was called MGI Technologies. So Mike Gascoigne is a veteran of Formula One. He had a consultancy company that really specialized in composite design. And we've rebranded his company Vertical Advanced Engineering. They're very focused on developing our composite structures, and really taking that technology from Formula One that I briefly touched on a moment ago, and looking to integrate that into aerospace. So the POC, if anyone has seen our website, you will have probably seen a couple of the slides that I'm going to show. It's a proof of concept vehicle. It completed its flights, and really it was just demonstrating that the company, that original 6 people and a few extras as they came on board, could integrate off-the-shelf equipment and complete a flight test program. It weighed in at somewhere near 750 kilos, maybe just over 750 kilos. And I think the battery weight for this, and this is an important topic which drives all of aviation weight, and the battery weight of this vehicle, I think, was about 350 kilos. From a product perspective, if this was to be taken forwards, it would be a single passenger vehicle with potentially some payload, some additional payload that could be utilized, but not really the groundbreaking, disruptive aerospace approach that Stephen had in mind. So we moved to Serif. Now, there's a lot of obvious differences between this vehicle and the previous. One of them is we've moved from a quadcopter, essentially, 4 rotors in shrouds, to a multicopter. This has 6 arms. Each arm has 2 props, and no longer shrouded. There's a few other differences internally. On the previous vehicle, on the POC, there is no redundancy in any of the systems. Here we're really looking at how do we ensure that after a failure we can continue safe flight and landing. So this is one of the cornerstones of aviation, and the phrase is no catastrophic failure can no single failure can cause a catastrophic event. So we keep that as a bit of a mantra throughout all of our design activities. So this vehicle, as I've mentioned, we're looking at redundancy testing. We also designed the rotors ourselves. You can't buy rotors off the shelf for a 2-ton, not 2-ton, sorry, 1.2 ton vehicle with 12 rotors. They don't exist, so we had to design our own rotors. That took a lot of simulation work before we actually built them, and then during the flight test we then looked to validate our testing, our simulation, sorry. And all the way through this, we are really focused on developing our internal company capabilities, as well as looking at improving the vehicle. So company design tools and techniques. Here we've got aerodynamic analysis. There's also a lot of electrical load understanding. So when one prop is spinning, what are the other props going to do? So what's the interaction of the flight controller with the different propellers and the interaction onto the powertrain? So I'll focus a bit more on the powertrain in just a moment. We wanted to create a vehicle that could take 2 passengers and some luggage. So we equated that to about 250 kilos. And actually this vehicle, it's pretty crude if you take the outsider away, but it met all those objectives. So it could carry the payload. It flew I think 80 kilometers an hour was the maximum speed, and quite critically we failed a motor and we were able to continue safe flight and landing. So from a redundancy test perspective, it was an extremely robust vehicle. I'm just going to touch on the powertrain now, as this is one of the focuses of the presentation. And what I really want you to take away from this section of the presentation is integration is absolutely key. There's nothing on the vehicle that is standalone that you can design in a closed room, and it will just fit onto the vehicle and perform. Really, integration is key. So if we just have a look at what we have in this photo, in this CFD analysis in the bottom left, we have 2 propellers. We're going to focus on just one propeller connected to a motor. The motor is then connected through the AC cables. So you see the 3-phase in the red and the blue, and I think it's probably black in the color behind. And the blue pipes are the cooling systems. Now, to design this system, we need to break it down into what are we actually trying to do, and then how do these things connect together. So we have the rotors, and they are producing lift. You've got a motor, and the motor is driving the rotor. I know some of this sounds obvious. The inverter is converting the HV from the batteries into an AC that is driving the motor. The motor and inverter need cooling, the battery needs cooling, the battery also needs venting. But you can't sit down and design this at this point in time. You need some more information. So the main information, this is clearly not all the information, but some of the really high level pieces of information are: what is the mission profile that we want to fly? What is the vertical acceleration in that mission profile? So we want to climb to 50 meters. How fast do we want to climb to 50 meters? If we want to avoid another vehicle in the air, maybe someone is flying a drone, how fast do we need to do that evasive maneuver? What's our horizontal acceleration? I talked about 80 kilometers an hour, which we achieve with the vehicle. As you're flying 80 kilometers an hour, how quickly do you need to maneuver? What maneuvers need to be made during that mission profile? All of that feeds into this system, and it feeds into this system by understanding the airflow from the rotor. The airflow we are using also is our cooling, so there's a really good link there between the airflow and our cooling capability. The motor is sized, and these are bespoke motors for us. They've got bespoke windings to ensure that the RPM is at the right speed, to the right value RPM for the rotors that we've designed, and we are able to control the temperature of those motors with this cooling system. The cooling system is also linked to the inverters not shown in this picture that are installed in the main body of the vehicle. So jumping through, what do we get out of this system? We get a powertrain weight. Weight is critical, so we get structural weight from the powertrain weight. So what structure, how large is that arm? How much load? What loads are we taking from the rotor through the housing, through the arm? The housing that is holding the motor is metallic. We've then got a composite arm, so we have an adhesive bond. What's the strength of that adhesive bond? So from the output of this exercise, we call the sizing exercise, we're getting essentially the aircraft size. We then want to have an available payload. In the case of Seraph, it's 2 people and a pilot, so there's 250 kilos. And then we need to actually understand how the vehicle is going to fly. So what are the flight control laws that are needed to control this? So from a flight control laws perspective, we're touching back onto the acceleration topic. When you want to change direction, which motors are going to be engaged? How fast do they spin? When you want to yaw, so yaw is twisting around the z-axis, the y-axis, which rotors are you speeding up? Which rotors are you slowing down? And then when you've gone through that exercise, you need to feed back into the beginning, because you don't know unless you put the numbers back into the start if you have closed the loop. So if the weight that you end up with actually enables the mission profile that you wanted in the first instance. So that closed loop is really important. What you end up doing from a design perspective is you iterate around this loop a number of times, hopefully coming closer and closer, making smaller and smaller changes. Sorry. So I've got a little video. Hopefully this will play, as I want to ensure there is proof that we actually were able to design and fly this vehicle. Oh, sorry, I don't know what's happening. So where do we go next? I think something that's quite evident is we've built 2 full-size vehicles. Learning from full-size vehicles is so much more extensive than it is from part-size vehicles, subscale testing. So we're going to follow that trend, and we're going to build another prototype, another full-size prototype. The previous 2 really were essentially a warm-up. We always intended to develop a winged concept. Now wings already exist, which is why winged concepts weren't a focus previously, and we were focusing on understanding the powertrain and the rotor elements. But now we have defined the vehicle that we're going to take through to eventually to certification, but take through to a full-size prototype at the end of 2021. So about a year from now, hopefully less than a year from now. And just to touch on some of the criteria for this vehicle. So 100 miles at 150 miles an hour. Now that sizes the battery straight away. That says we need to have 45 minutes of flight, maybe slightly longer because you don't start at 150 miles an hour. And we also need to have a diversion. So already, first requirement, we're defining an element of the aircraft. 1 pilot, 4 passengers. There's our payload. Again, that defines the weight that we need to carry for that period. We also now have a size for the fuselage. All electric, so we will use batteries. We're not quite there with hydrogen yet, I don't think. So we're on batteries. Low noise to blend into the city life. Now, if anyone's heard a single rotor aircraft fly over their house or a helicopter, these things are not quiet. Noise is a real big factor when it comes to aircraft operations. The example I often draw is in London. There is a helicopter pad in the centre of London at Battersea. That's limited to 6 flights an hour, and the limitation is noise, and it's about disturbance. So if we can reduce the noise of the vehicle, that 6 flights an hour straight away goes up. So there's a clear benefit in focusing on that. Canary Wharf to Heathrow Airport in under 20 minutes. So this is actually drawing on a different requirement. So in the top left, we have a one solid mission of flying 100 miles. Now, under 20 minutes, we're talking about a shuttle mission. So that gives a different mission for us to work to. So in my previous slides, I was looking at this mission and the accelerations, etc. We've got two extremes of mission that we're going to focus on with this vehicle, and significantly more affordable. There's no point in creating this lovely new vehicle if it's going to cost you twice as much to fly on it. Nobody will use it, so it needs to be cheaper. We're actually targeting about $5 to $6 a mile, which is extremely cheap. So that means your flight from Canary Wharf to Heathrow is in the 50 £50 bracket, not the 2,000 plus probably that it would be for a helicopter. So a real step change in the cost. And a lot of that is down to the electrical powertrain. I'd like to just draw attention to the same system, but the additional complexity that we now have in our new vehicle. So I don't know if anyone noticed. I'm sure it was picked up. In our layout now, we have 8 rotors, not 12. And the forward 4 are tilting. So you take off and they're all in the vertical position, and then to go to forward flight, those front 4 transition. Now we've settled on 8. This is really down to understanding failures. So that phrase I mentioned at the beginning, no single failure can cause a catastrophic event. If we were to lose any motor, any rotor, we are able to still continue safe flight and landing with the remaining 7. It doesn't matter which failure it is, any failure we can continue, and that's a really critical point. If anyone wants to certify a vehicle, that needs to be demonstrated. And 8 we believe is the minimum number. So if you were to go down to 7 or 6 or 5 rotors, it starts to get harder to demonstrate that one failure is a survivable event. So with this addition, we now have a tilt mechanism. So the addition of this moving prop, the moving rotor, we now have a tilt mechanism. So the rotors are no longer just lift, but they're also cruise. So that cooling system that we looked at in Serif needs to accommodate 2 different phases of flight, 2 different orientations of airflow. The EPU, so this is the electrical propulsion unit, that is comprising the motor and the associated cooling system. One day it might also include the inverter, but at the moment ours are still separate. The propellers and the rotors and this tilt mech, it all makes up this one system that we've defined. And I think it's quite obvious, but just to highlight, this is what's happening. We have an actuation between the forward thrust and the lift thrust, but this is putting huge loads through this section of structure. So from an integration perspective, and talking about you can't design in isolation, we now have huge gyroscopic loads that are being transferred from the rotors through a tilting mechanism along the structure and into the wing. which creates a huge issue for us to manage, a huge engineering challenge for us to deal with. And just to highlight the addition of this in that the fairly basic system design I put forward earlier, we have the lift rotors mounted on the motor, the inverter, the cooling systems all need to be integrated with this tilt mechanism. So the tilt mechanism needs to have dynamic HV cables, AC cables, cooling systems, whatever the final design is, it needs to enable this dynamic movement. And it needs to react to the structural loads. So from a weight perspective, closing this loop is an additional challenge for us to solve. But as with electric cars, really electric cars are just batteries packaged in a car. They just happen to be in a car shape. Really, here we are a battery just packaged in an aircraft shape, because the battery is the largest system, the heaviest system on the vehicle. It's probably going to be about a third of the vehicle weight in its entirety, and it also presents one of the not the only, but one of the biggest challenges that we have to solve: integrating a battery system into the vehicle and all the complexities that go with it. And one of the questions that I often get asked is, why can't we take a Tesla and strap it on the bottom of our vehicle and away we go? Well, as good as the Tesla battery is, it's not designed for aerospace. Firstly, there's no redundancy. So imagine a cell failure at any point, and in your downtime, feel free to Google EV car fires. You'll see plenty of examples, unfortunately. Interestingly, more around charging than discharging, but they exist. So what happens when we have a failure? So a cell goes into thermal runaway. So it could be an internal failure to the cell. There could be some debris inside the battery for whatever reason, and or it's taken a bump and there's some damage, and it creates a short circuit, and that leads to thermal runaway. A cell sets on fire. It burns maybe for a couple of minutes at about 600, 700 degrees C, possibly higher as well. It becomes difficult to measure, and invariably it will set the next cell on fire, and then the next cell on fire, and you have a cascade effect. And the beauty of a car is you stop and you get out, and it actually doesn't happen quickly. It's not an instantaneous explosion as you would have with jet fuel or petrol, but it happens quick enough that you want to stop and get out. We can't have that in an aircraft. Stopping and getting out is not so simple, and if this event starts to happen on the vehicle, we need to be able to still draw enough power to be able to land the vehicle in a safe manner. Sticking to that phrase, no single failure can cause a catastrophic event. I should qualify: catastrophic is not good. You're looking at losing the vehicle and losing passengers. So this really is a focus for aviation. Now, Tesla, the pack is an extremely powerful pack for automotive. It's 168, I think, give or take, kilowatts per kilogram. That's not enough for us. We need a higher power dense pack. Now, interestingly, cars, it's much more about range. The focus is on energy density. So the cells that are going to be produced more and more for automotive are not necessarily going to be the cells that will suit aviation. as we need power, that the vertical takeoff period of the vehicle really draws huge amounts of power, and we can see that in a couple of slides, I think. So the automotive power density is not enough for us. Cooling, actually I'd like to refer to it as heat extraction. When you're in an energy draw situation, not a power draw situation, you can maintain the temperature of the pack fairly well. It's drawing the power that creates the heat, and what we're finding is we're drawing so much power and so quickly. Being able to extract the heat is very difficult. So we are having to design the pack really to cope with that raise in temperature and not expecting a very fast extraction of heat. Structural integrity is another challenge, and actually this is around trying to achieve a higher power to weight ratio, so this kilowatts per kilogram. So this Tesla pack, it's designed to be the underside of a vehicle, so any debris from the road can come up and strike the pack. We don't need that on an aircraft, so we can actually have a much less robust structure than the Tesla. So straight away, without changing the cells, but changing the casing, we could improve the power to weight ratio. And also the parallel and series layout. So here you're looking at modules that are arranged to give a specific voltage and a specific current. Now we're looking in the aviation arena to move the voltages from around the 400 volts, which most automotives are at, to around the 800 volts. Quite interestingly, Porsche are pushing or have an 800 volts vehicle. And really, you get benefits from weight with going up in voltage. There is always a trade-off, so creepage and clearance, so the distance that electronic components can be has to increase. And that makes things larger, and larger means heavier. So there is always a balance. But also, I didn't want to list everything, but I really wanted to draw attention to the fact that this Tesla pack is designed to automotive requirements, not aerospace requirements. And when we look at the aerospace requirements for these vehicles, eVTOL vehicles, electrical vertical takeoff and landing vehicles, for us to run commercial operations, we need to meet a failure rate of 1 failure every 10 to the minus 9 flight hours. And that's really very high. That's a really very difficult failure rate to meet. It's equivalent to a standard large aircraft aviation, so your A320s, A350s, sorry, I'm Airbus, Boeing 787s, etc. They meet this very stringent requirement, and you can't meet that through testing at the end through just a solid design process. You need to implement processes and procedures to integrate what's called design assurance. So you know that when you follow this process, you get a safe design at the end. And actually, the aviation requirements, they are all about defining process. If the vehicle is not flyable at the end, is too heavy, that's actually not EASA's issue. It's not the FAA's issue. Their issue is ensuring that you can produce safe aircraft. So we'll keep in mind those aviation requirements. This is an example of a pack that we've designed. We've actually not taken this through, and I'm sorry I can't give too many details around this pack. the battery design, as in the automotive world, is going to drive performance of the vehicle, and therefore it does bring a pretty good competitive advantage if we can outperform our emerging competitors. But really, I'd like to draw on a couple of things. Firstly, we're looking at having multiples of these packs. So this is one of a number of packs that are all going to work together. And inside the packs, we have modules. Now, that's actually not so dissimilar to the Tesla. If I jump back, here you can see in this pack a number of modules. What we've done is we've got modules inside packs, and then we've got a number of packs. So if you have a failure, a fire, it will only take away one pack, not all of the packs. And we have a number of requirements that I've summarized here into having a minimum weight, maximum power. So this is, again, this power to weight ratio, 168. It's good for automotive. We are pushing over the 200 kilowatts per kilogram. One of our competitors, Joby in the States, I think they are talking around the 235, 238 kilowatts per kilogram region. We'd be happy if we achieve that as well. That's a good target to set. So how do you go about designing this pack? So I talked about heat extraction, and it really is all about heat extraction. I would just like to make a note, these values are hypothetical. They are not a direct extraction from the vehicle we're designing. But let's say we need to draw 1.4 megawatts of power for our eVTOL phase. The thing that cuts us off is this temperature line, the temperature line that is consistent across the three graphs. So we are fully designing around temperature. So how we control that temperature, how we're drawing the power, where the temperature is coming from. The cells are an obvious source, but then the distribution of electrics inside the pack is also a source of heat. And the maneuvers, you can see the maneuvers that we are now coupling to this temperature increase. So takeoff, vertical takeoff, climb, hover, these are all in the vertical phase. As soon as we move to conventional flight, the power draw on the vehicle drops off really quite a lot. So it's not been so much of a focus from a sizing perspective. We need to be able to complete a vertical phase of flight. And we also need to be able to complete a vertical phase of flight when we lose a rotor and lose a sub-pack failure. So this is one of the battery packs. So if we use I'll use the example on the right. In this simulation that we were running, if we lost one of the battery packs, the power draw is such that it is going to, during that second yaw, or that, in this case, sorry, the first yaw maneuver, the temperature is going over the 65-degree cutoff. And it's actually, I think, around 85 degrees that thermal runaway is a potential. So we have a safety margin in there. But clearly, this is not a good situation in that right-hand graph. So we need to maybe increase some additional cells, add some additional cells in there to distribute the power more across the batteries, or look at ways we can extract heat more efficiently and more effectively. So this just gives a flavor of that cycle that I talked about before, which is understand what you want to achieve with the vehicle, design your powertrain system, understand what you have after that. So what have you designed, and then feed that back into the start of this design loop. And to touch on the regulations, because aerospace is heavily driven by regulations. If anyone has ever worked in the industry, will know we're doing everything we can to draw from other industries. I touched on the Formula One quite specifically earlier, but we have a lot of experience from Dyson, from Jaguar Land Rover, from other land-based kind of system designers as well, to look at essentially streamlining how we can achieve the aerospace requirements. But you've got three kind of levels. The first one is called Part 21. This is, how do you define an organization that can design aircraft in a safe and robust way? So there's the organizational requirements. So what roles and responsibilities are within the company, who does the design work, and then who checks that design work, and then who oversigns that, who's taking ultimate responsibility and accountability. It's all defined in this document. The middle document is the special condition that has been created for vertical takeoff and landing aircraft. This is because it's a novel vehicle. It does not fit into the standard requirements that EASA has already defined. And it's exactly the same situation for the FAA. EASA being European, the FAA being the American, and generally driving the global aerospace requirements. And these aircraft design requirements, they define essentially everything around the vehicle, but they don't tell you how to do it. They say we need the vehicle to be safe in this condition. We need to ensure that the vehicle can has sufficient flight after a failure to get to a diverted landing point, for example. Really, how you do it is then defined in acceptable means of compliance. I've drawn out the battery one here, but really this is a suite of documents that if you follow, then you will be in line with the special condition. One of the unfortunate things with eVTOLs is actually the requirements are not fully defined. Therefore, the applicable means of compliance, the typical means of compliance, are not and are also not fully defined. So in a lot of these instances, when we're passing through this design loop and trying to understand how we want the systems to behave in certain scenarios, we are also having to work with the authorities to define what those requirements are. Our internal battery specialist is actually leading the rewriting of this this battery document, DO311A, and that's defining things like, if you were to drop the pack, what do you expect to happen? If the pack overheats, what do you expect to happen? What are the charge rates? What are the different conditions for charge, etc.? And so it's a very all-encompassing document. So they're kind of the main focuses that that we're working on. Now, just to kind of look forwards over the next few years, for vertical aerospace, and I guess actually all the other eVTOL aircraft designers, we're looking at designing and developing our full-scale prototype. We will also design and develop a number of test rigs, and this is about validating and verifying our assumptions. So we believe that a system will get to a certain temperature based on our simulation modeling. We then create a test rig and we prove that it does get to that temperature. So that will happen. The vehicle will be built throughout the second half of next year, hopefully flying before the weather comes in. So around the September, October time, we'll start test flying that vehicle, and the flight test program will run for about 18 months. In that time, we will achieve our what's called DOA and POA. So just referring back to the Part 21 document that I mentioned on the previous slide, we have the Design Organization Authority and the Production Organization Authority. So this is the CAA and EASA agreeing that we have all the processes and procedures in place to design and build aircrafts in a safe manner. So that's really critical. If we want to be an aircraft manufacturer and an aircraft supplier, then we need to have that legislation in place. The prototype, it's not going to be quite good enough for certification. It's a stepping stone, a technology stepping stone. So we will start the design actually probably by summer next year of the certification vehicle. And that will be taking everything that we're learning from designing this latest prototype, improving it, improving the safety, improving the integration, saving weight critically in every area, and then starting the certification activities. So we will have the first certification standard built by the beginning of 2023, and then we have approximately a 2-year window of flight testing, and this is a really time-consuming but clearly critical area where every eventuality of flight condition needs to be explored to prove that the vehicle is safe to enter service. And then at the beginning of 2025, everything's perfect. We have a vehicle and it's ready to sell. But unfortunately, the problems don't stop there. The vehicles, I apologize, I've only used serif in this slide. I pinched it from somewhere else. But the vehicles need an infrastructure to integrate within as well. It's not just about creating an aircraft. We need to enable, and we're not going to do this all, we need to enable other industries to develop the whole infrastructure of this emerging aerospace. So if we just work from left to right on this slide, we have what we're calling vertiports. Now we need chargers. How many vehicles are going to be charging at once? What kind of maintenance activities needs to happen? Clearly a very different operation than a helicopter operation. We want to take credit of the latest standards of technology, and 4G, 5G is just an example of that. How are the vehicles integrating into the emerging networks that are being investigated and invested in at the moment? How do the vehicles communicate to the Air Traffic Control Service, ATC service? How do the vehicles communicate with other vehicles in the air? So TCAS is an example of that. But how are we going to draw on that technology and then hopefully take it to the next step? How is it integrating with what's already on the ground? So the ground-based systems and sensors. So if we fly over a radar of an aerodrome, do we disturb that signal? Does that signal disturb our vehicle? Those things need to be integrated. So moving to the right, integration to airport security. In theory, we should have a lot more people being able to travel via air transport now. How are the airport security systems going to enable that? And anyone passing through an airport knows it's not a very fast activity. So we need to enable something to enable this additional throughput in vehicles, in passengers, sorry. And we've also got the integration with already established aviation. So how does the latest technology eVTOL vehicle talk to the old aviation vehicles that are flying? So a Cessna 182, for example, that might not have all the bells and whistles and might not be able to communicate in the way that the latest technology is driving. And just another note, which is actually an increasing issue, I'm sure people have seen in the news, is the interaction of drones within our airspace. So how's that managed? And drone services are going to come online. Companies like Amazon are going to use drones for cargo delivery. How is that integrated into this overall, I guess, system of systems? So my finishing words really are: the vehicle is a very complex problem to solve, but it's not the only problem to solve if we want to fully enable the eVTOL market to be established and to be profitable come 2025. So thank you very much for listening, and I think I'm handing back over to Andrew. So thank you.
Thank you for that, Lawrence. That was a really interesting presentation. I think it's generated quite a lot of questions, and it's clearly an area where we're making some great developments, but there's still unanswered questions in how that's going to apply in real life and into a commercial system. So thank you for that. If I can just start off with a question of my own, could you give us a sense of, I know you might not be able to give an exact figure, but the power requirements for vertical takeoff, for example, for your vehicle?
Yeah, sure. If anyone with a sufficient mind were to sit down, it's not difficult to equate the weight of the vehicle to a power demand. So it's not necessarily that much of a problem to share. So the legislation allows us to go to a 3.15 ton vehicle. And for vertical takeoff of that vehicle, you're looking in the region of about a megawatt, up to about maybe 1.2 megawatts.
Okay, thank you for that. So we've got 23 questions. I won't be able to go through them all in this session, but what we will do is send out a written response to some of these questions that we don't get a chance to answer. And we've got the distribution list for everyone who's attended. So first question, this was from Paul Ellis. Have you considered removing the pilot, which allows additional passengers?
Absolutely, and a really good question. There's a company called Whisk that are actually linked to Boeing that are focusing on this. They believe it's a really good route to market. The vertical aerospace position is that we don't think that the legislation is going to enable pilotless flying in the short term. So if we go to driverless cars, there are a lot of vehicles out there that you would say now have the ability to be driverless, yet still the legislation says that the driver needs to be able to take control. It's going to be a similar kind of slow approach, we think, at vertical for the pilotless to come into the loop. There are elements, so I'm specifically saying pilotless. You could move the pilot onto the ground, so the pilot is no longer in the air. So you have a pilot sat in a seat, essentially flying a simulator, but that simulator is an actual vehicle. You could have that situation through to fully autonomous. So it's not necessarily autonomous flying that will come first. But the technology is maturing. We're actually part of a consortium for a UK competition called César that is looking at some elements of autonomy. I think it's looking at doing an autonomous takeoff and then an autonomous land, but not a full autonomous route. So it will be explored, and it certainly will be the future. In 20 years, I'm sure they will all be autonomous.
Thank you, Lawrence. I suppose perhaps we'll see autonomous in small cargo eVTOL applications before we see it in passenger aircraft. So
yeah, completely, and really, it's the regulations are driven around safety. If you have a route that doesn't fly over people, no one's on the vehicle, then you can imagine autonomy is a lot easier to integrate than if you're flying passengers over schools, for example.
There was the next question's about the helicopter controls, and there was actually another question on a similar vein to that. So, are the controls similar to those in a helicopter? And just adding in the other question about training, so pilot training for controlling this as well.
So, pilot training, I would touch on that first. It's an extremely difficult topic, and it's a real chicken and egg topic. So these vehicles don't exist, so we can't train the pilots. They will exist in a relatively short amount of time, and at that point we need probably hundreds of pilots to be starting to train. So where is this influx of pilots going to come from? Are we going to be able to enable that? It's a really difficult topic to answer. And actually, I was on a call with NASA yesterday afternoon talking about this very topic, and they're looking at writing a white paper that will focus around this, or that's an element that they'll focus on. Now, with respect to helicopter controls, yes and no. So if I draw to what the pilot sees, when you're in a helicopter, you have a collective. So you've got a lever that is that is doing your vertical movement. You then have a joystick that's doing your attitude, and you have pedals as well that's doing that are doing controlling your yaw. Now, as you move into conventional flight, you're no longer controlling through the rotors. You're controlling through the wing surface control, so the ailerons and the flaps and things like that. So the connection changes. So yes, it is similar. The way the control is done is different though. So if you're looking at yawing in a helicopter, you use the tailplane, and the tailplane is yawing the vehicle. In a multi-copter, generally you're using changes in the rotor speed. So you're using the inertia of the rotors to create a yawing moment. You can also angle the propeller slightly to also drive some yaw control. So the pilot will have the same controls in the vertical flight as a helicopter. He'll have the same controls in the conventional flight as an aircraft. So here's a pretty big challenge for us to solve. But in the vertical flight, how the vehicle is actually controlled is different to a helicopter. I hope that answers the question, or maybe raises more questions. I don't know.
Possibly raises more questions, but no, I think that was a good answer. Thank you very much. I had a few people actually ask about removing the shrouds on the rotors, so going from the ducted fan to an open design.
A really good question, and they were actually some of the slides I cut out because it's a really obvious difference between the POC and Serif, and you get some benefits of the shrouds. So just to touch on the benefits, from a noise perspective, they're really good at containing the noise of the rotors. You also generate lift from a shroud. So the shroud is essentially a wing. So as the air is being sucked in by the propeller, you're creating lift. And if you have a rotor failure, you could imagine that the shroud can contain that rotor failure, just like in a jet engine, and some of the blades, not all, but some of the blade stages can be contained by the engine, by the shroud. But they're heavy, so we have a weight penalty, and they also act like a windbreak as soon as you start forward transition. So any forward motion, and when we flew the POC, I think we were about 15 degrees to actually get any forward speed, any decent forward speed. And from a passenger experience, this is quite a change in the attitude of the aircraft. And I think it's about 5 degrees, maybe even slightly less, when you remove the shroud. So it's making a really big difference for that initial transition phase. And going back to the powertrain, you need a huge amount of power to overcome that drag that is being created. So it's an additional burden on the battery and the HV powertrain, etc., and the motors. So that's really primarily why we remove them.
Thank you. You also mentioned about the single event failure for one rotor, and there's a few questions on that kind of topic. So, sorry, let me just find one. So, how is a single type failure avoided? Different equipment, diversity, etc. So I think this is more along the lines of how do you ensure that multiple rotors don't have a similar failure mechanism at the same time?
Really good question. So the title for that topic is common mode failure. And just some examples of what a common mode failure could be. So it could be at a temperature, a bearing fails, or a seal fails or something. So if you're taking off at minus 20 degrees in Canada, the bearings are always going to fail because they're too cold. So that could be an example of a common mode failure. Another example of a common mode failure, and it's one that we're in quite heavy discussions with the authorities on, is what happens if you lose a blade. So a blade fails and it hits an adjacent blade, which hits an adjacent blade. So you have a cascade effect. So it's not, they don't all fail at the same time, but it's a cascade effect of failures. So we need to treat both of these topics, the common mode failures and the cascade effect. So from a common mode, the approach is generally, it's not perfect. There's a lot of techniques. It's a huge topic, which I'm not going to be able to fully answer just in this call, but we need to basically design away the common modes. So we imagine what are the common modes between. So in a motor, it's the bearings, it's the magnets, it's the windings. And then we look at what are the external influences that could cause a failure. Now, if we can ensure there are no external influences that can cause that failure, and now we're just looking at it, they might fail after 10 to the 5 flight hours, they won't all fail at the same time at that point. So you'll have one failure at the end of a bearing life, but that's not going to be at the same minute after you've been flying for 100 hours as the other failures. But you could then start introducing things like maintenance rotations. So you're replacing things more systematically and maybe out of sequence to ensure that things aren't coming to the end of life at the same time. And the cascade effects, really, it's around analysis. And there's a lot of aerospace processes and procedures around following failure hazard analysis, system safety analysis, failure mode and effect analysis. So these things, they help in identifying the common mode, the cascade failures, as well as it's just generic failures. But the cascade effects, the propellers are an easy one to see, but you could have a short circuit. That short circuit could draw a lot of power from the battery. That in turn could cause a battery failure. That means the other batteries are now more overloaded. So now we need to understand if another battery pack is going to fail as well. So it's really sequentially thinking about what are all the failures that could occur, and in each failure instance, how could that impact the surrounding systems, and how are we going to treat that? So it's extremely, I don't want to say laborious because it sounds like we don't want to do it. It's critical, and it's one of the main parts of aviation, is actually analysing each potential failure, analysing each part of a system. How could it fail? What could cause that? And what are the repercussions of that happening?
Yeah, really clear. That's a really complex issue, and
Very much so.
I guess the processes that are currently available within aerospace for helicopters and even for your commercial airliners
Yeah.
are applicable here in
And
terms of failure mode propagation.
and actually, one of the main benefits of moving to electrical propulsion is to make vertical flight safer. Helicopters actually have a failure rate of about 10 to the 5, and that's really around the gearbox, very complex gearboxes, very complex gas turbines. I should caveat that the more complex and the larger helicopters actually are better than 10 to the 5. I'm talking more the small helicopters. And when you introduce electrical systems, you're able to remove a lot of the complexity, and with complexity often comes failures. So once you remove the complexity, you have a much more simple system. On our vehicle, the only moving part is the motor. That's it. There's no other moving parts. So you can probably imagine that's extremely simple compared to a helicopter.
Exactly, and I think that drives the desire for electric propulsion throughout the entire
Absolutely.
aviation industry, and even in automotive too,
Yeah.
for servicing. You mentioned some standards there for certification, and one of them was the DO 311A,
Yeah.
lithium ion battery standard. There's a comment that that's not currently under revision. Can you clarify what work's being done around the standards that were mentioned?
Yeah, of course. So the official release of DO 311A is called Amendment B. There's actually an Amendment C, which is not an official release, that clarifies some of the testing, but it's currently in revision. It's in Euro CAE, and it's working group 112. And I think it's 112, and that's looking at rewriting. It's not completely from scratch, but some of the elements of there to look to make the tests more representative of the batteries that are going to be used. So it was originally written to facilitate batteries in general aircraft, where the battery is a source of backup power, essentially, rather than the main source of power, which is an engine. So there are some differences in when it comes to the failures associated with those packs. So if they want more information, Euro CAE Working Group 112 is where to go looking.
Thank you for that. There's another question on the battery development about fuel cells, and would you consider fuel cells as an alternative to the lithium battery approach?
Yeah, for sure. I think what I will state is we're very unlikely to develop our own fuel cell, but there is clearly a lot of interest and increasing traction around fuel cell. So in the UK, at least I know, there's a company called Zero Avia that are investigating fuel cells. In my time previously at Airbus, there was a number of projects looking at fuel cells, so I expect that's continuing. There's a lot of automotive interest in fuel cells as well. But with fuel cells comes additional complexity. A battery, it sits there, it produces, you can draw power from it, or not. That's it. There's nothing else happening really. With a fuel cell, you have quite an additional added complexity of containing your fuel in a safe manner, which is not so easy to achieve. And then you need additional systems on how do you purge stacks, how do you keep pressures at the right level, etc. So I expect it will come. It's not a simple solution, and really we're looking at how do we get an eVTOL to the market as quick as possible. I'm expecting the first fuel cell solutions to be coming out for aviation in around 2025. Now we want a vehicle certified and going into operation then. So the battery is the way to get there in the first instance.
Yep. Yes, that's they're on the horizon, but they're not quite ready yet.
Yeah,
with fuel cells.
yeah, we're certainly keeping a watching brief.
Yeah, and with batteries, obviously you have to cope with the discharge range of the battery as well, which makes optimization of the inverter for your motor drive a little bit more complex, because you have to consider the voltage range.
Yes.
Are you going? Is it currently an unregulated DC distribution, or is it regulated at the 800 volts?
So it's, I guess, regulated. So we are actually just under the 800 volts. So we say 800 volts, but it's actually just under. And depending on the chemistry of cell that you select, you have your discharge profile, and then you need to design the inverter to match that discharge profile. So if you're starting at 800 volts and you're using let's say LFP as a chemistry, I think LFP is a pretty flat discharge. So maybe it's actually only 700 volts before you drop off the cliff. So you only need to design for that 100 volt range window in the inverter. Whereas if you're looking at a different chemistry, sorry, it's not my area of expertise, but a different chemistry, you could see a lot quicker a drop in that voltage. But when we're looking at that flight duration, it's trying to predict, particularly if there's a flat voltage discharge or a flat voltage during the discharge, it's trying to predict when the voltage is going to drop off the cliff and diminish to an unusable value. That is the key in trying to understand and trying to define to the pilot how much time he's got left. So the difference between 710 volts and 700 volts might be half a second, or it could be 5 minutes. And where are you in that range? It's not so easy to develop.
Thank you. I think we'll take just one final question, and they're still coming in, Lawrence. So I'll send you the list over after this, and we'll reply to them.
They're not all coming from Vertical Aerospace, so they should know the answers.
So given the high voltage and current being controlled, has EMC been an issue?
Yes, absolutely. So EMC and I guess I'll also just mention static as well. So EMC by virtue of we need to turn AC to DC, DC to AC. So that section from the inverter to the motor is a very electrically noisy environment. So we need to reduce that as much as possible, but the motors themselves are obviously going to generate a lot of EMI to try and manage. So we can't stop that being produced. So we then look to screening, we look to filters on systems, we look to getting communication signals out of the same frequency as that EMI. So it's there is a lot of interference being produced, but it's not unmanageable. There are tried and tested ways to manage this. But from a static perspective as well, we now have 8 rotors, not just a single rotor, all of them producing static. So as soon as something's moving in air, you're going to electrically charge the vehicle. So we now need to manage the ground plane of the vehicle, and how we couple things to that ground plane or don't couple them to the ground plane is quite important.
Yeah, clearly quite a challenge. So I guess that's why it's really important that we do these kind of demonstration vehicles and
Absolutely,
develop that learning.
yeah. Uh,
Fantastic.
I will just add, when you have a composite vehicle, it becomes harder to manage these things. Metallic vehicles are a lot easier. So having metal mass is a real benefit that we just don't have in a composite vehicle. So that is an added challenge. Sorry.
Thank you, Lawrence. And with that, so the rest of the questions that we haven't been able to answer today, we'll follow up with an email to the attendees just to try and answer those as best as we can. And with that, I'll hand over to Martin.
Thank you.
Thank you, Andrew. Well, Martin Woodcock, Vice Chair of the Midlands Power Group. Right, well, it's amazing to me anyway, just what vertical aerospace have achieved since 2017, especially as you've progressed the design, build and testing of not one but two prototypes in that time, in an integrated systems approach, and also fascinating to see what you're planning for the future. So on behalf of the Midlands Power Group and everyone on the call, it just remains for me to thank you, Lawrence, for a thoroughly interesting and enlightening presentation.
My pleasure.
There are a couple of closing points. So firstly, CPD certificates will be emailed out for everyone attending within the next week. Apologies for anyone that attended our last event and hasn't yet received a CPD certificate. That there is a slight backlog there that we're going to get addressed. And lastly, the Midlands Power Group, our next event is titled DSEAR, Achieving Electrical Safety in Hazardous Environments. And that's provisionally scheduled for the 26th of January 2021. That may change, but please keep an eye on the IET events page for anyone interested in dangerous substances and explosive atmospheres regulations. Okay, right. So we'll bring this call to a close, and thank you everyone for attending.
Thank you very much.